Chapter 7 is optimal risky portfolios. So what we're doing is we're building a model for asset allocation. We're going to build a model in stages by incrementally expanding the investment universe, starting with a very strict universe, and then slowly remove the restrictions until we get something that looks more like real life. And the whole idea is to come up with some way to figure out how we allocate wealth into investable assets, how we build a portfolio. So we started with two available risky assets, and we said you can put 100% in one or you can put 100% in the other, and that was relatively easy. There was either dominance or we went through utility. Then we let one asset be the risk-free and the other asset be a risky, and we restricted allocations to 100% in one or 100% in other, straight up utility. Next, we got a little bit more complicated. We said, well, let's let there be one risk-free asset and one risky asset and allow any allocation between the risky and the risk-free. And we said that the set of possible allocations, the things in which you could invest, we called the capital allocation line. And we chose the optimal combined portfolio, which lies on the capital allocation line, by computing Y to maximize utility. And here's an example that we just did in the last chapter. We had our investment universe. The risky asset was at 1020. The risk-free was a 3% asset. We said, okay, we have an investor with a risk aversion level of 7. So the first thing we do is we figure out what the capital allocation line looks like. It goes from 3% to 10% and 20%, and then we did a bunch of math to show that this has to be a straight line. Then we figure out where we want to be on this line by finding Y star, which was equal to 0.25%, and therefore 1 minus Y star is 75%. So we have 25% of our wealth in the risky and 75% in the risk-free. And then we said, let's describe what this C portfolio looks like. This is the expected return of the C portfolio. The return is 475. Here is the risk of the C star portfolio. It's 5%. And we said, let's also figure out how much utility we found. And that was 0.0388, which has a certainty equivalent rate of 3.88%. And what this means is, for this investor and this investment universe, there is no better allocation. There is no better way to invest in anything else. Remember, all you can invest on is the line, given that you have this and this. And this is the best spot on the line. Anything else is going to produce a utility curve, which is below this utility curve. It'll have less utility. So the next step is to think about P. So far, we've said P is a specific, well, we've called it a portfolio, but we've given you what the risk and return were, 10% and 20%. Well, let's see how we find out what P is and how we find out how to calculate P. And we do so by starting with two other stocks. We're going to start with a stock here and a stock here. Then we're going to see how do we end up at this spot P. First, what do the allocations between these two stocks look like? And then where do I want to be on that allocation line? So next, let's let the risky asset P, really a portfolio, be comprised of two risky assets. And we'll determine the optimal allocation between these two risky assets and the risk-free asset. And then after this, the last thing we'll do is we'll say, okay, we used to let P be 2 assets, let's let it be 3 assets or 4 assets or 6 assets or N, some countable number of assets. So we're going to work on number 4 now. So the investment universe up to now has been one risk-free, one risky portfolio, and together they form a number of combined portfolios that are on the cal. We solve for Y to find the utility maximizing combined portfolio, C star. Next, what we want to do is we want to allow for 2 risky assets. And when you want to see how these 2 risky assets form a risky portfolio P. So let's assume asset 1 has a 13% return and a 20% standard deviation, and asset 2 has an 8% return and a 12%. So this is the 1320, this is the 812. Now there exists some correlation between them, we just don't know what it is yet. We don't know if these two stocks are in the same market and they're extremely correlated, or if they're in unrelated businesses and the correlation is lower, or if they're in opposite businesses and the correlation is negative. So for now, let's just leave the correlation unknown. So what we're going to do is we're going to plot the allocation line between risky asset number 1, which is the 1320, and risky asset number 2, which is the 812, and we're going to do this as the correlation changes. And what we want to do is determine for a given row where we want to end up on this allocation line. And this will give us the optimal P as defined by the optimal weight in asset 1 and the optimal weight in asset 2. So let's start with the portfolio risk equation. And there's a lot of math in this chapter that really proves and derives this. We're going to sketch the proof, we're going to sketch the derivation, we're not going to go into a ton of depth on the math. And really what I'm interested in is the resulting formulas, not necessarily the derivation of how we got there. I want to show you, I want to sketch a derivation, so this isn't magic, but I'm not super interested in you repeating this derivation to me. Okay, so let's start with portfolio risk, which is the standard portfolio risk equation. The weight squared, risk squared, weight squared, risk squared, 2 times the correlation coefficient between them, weight, risk, weight, risk. And for now, we're going to let rho equal 1, which is the highest it can be. They're perfectly positively correlated. When 1 is at its maximum, the other is at its maximum. When 1's at its minimum, 2 is at its minimum. And wherever they are in the range, they're working together. They don't have to have the same amount of risk, but when this one is earning its most, this one has to be earning its most. And when this one's earning its least, this one has to be earning its least. So they have to be moving together. They just don't have to move the same amount. Another way to say that is just because rho equals 1 doesn't mean sigma 1 equals sigma 2. The first stock can be riskier than the second stock. Now we know that when rho equals 1, we saw the math before, this term drops out, the 1 drops out, and we get an a squared plus b squared equals 2ab. And we solve for that, and we get this relationship where it's the weighted average risk. And so if it is the case that the stocks have 0 diversification, that they're perfectly positively correlated, there is no risk benefit from combining the assets, I just end up on this straight line. Remember that to the right is more risk and to the left is less risk, and what we're going to see is as I allow this correlation number to become smaller, I'm going to be able to achieve the same return but with less risk, less risk, less risk. And so for stocks that are almost perfectly positively correlated, I'll be just a little to the left. If they have very low correlation, I'll be a lot to the left. And if they have negative correlation, I could be way over here. And so what we're going to do is we're going to calculate what is known as the efficient frontier. The efficient frontier is what this allocation looks like for these 2 assets. And we could sketch these, we could do a bunch of math, we could try to figure out the minimum variance portfolio, but let's just talk about it very briefly and then we'll use Excel to plot these. So here's the idea, is what happens when rho gets smaller? Here is rho equal to 1. When rho gets smaller, I know diversification lowers risk. I know that lowering risk means that I move to the left. It means that this line has to move further to the left. Now, if I'm in asset 1, I'm going to be here regardless of the relationship with asset 2. And if I'm in asset 2, I'm going to be here regardless of the relationship with asset 1. But as I move out of 2 towards 1, if it's the case that there is less risk, I'm going to have to be over here somewhere. So let's talk about what this looks like, and let's talk about how to plot it.